Welcome, Ronald Lui.
Thank you. So first of all, I'd like to thank the organizer for the kind invitations. So the title of my talk today is Recent Advances of Computational Quasiconformal Geometry in Imaging, Graphics, and Visions. So over the last few years, together with my collaborators, I'm very interested in the topics of computational quasiconformal geometry and try to find its application in imaging, graphics, and visions. So today I'd like to give an overview of the work we have done in over the last few years. So this research project is joint work with a number of people. Tony Chan, who was at UCLA, and now he's at the Hong Kong University of Science and Technology. Xin-Tung Yao from Harvard University. David Gu is my longtime collaborators from Stony Brook University, and as well as some of my graduate students, most of them are now in US. So this is the outline of my talk today. So I will first of all talk about the motivation of this research project. Then I will talk about some basic mathematical background about quasi-conformal geometry. Then after that, I'm going to talk about how computational quasi-conformal geometry can be realized on discrete surfaces. So in particular, I'm going to talk about how quasi-conformal geometry can be formulated on discrete surfaces. And then I'm going to introduce some computational algorithm for computing the QC maps. And then in the second part of my talk, I'm going to talk about some applications of QC in imaging, graphics, and visions. So let me start with talking about the motivation of this research project. So the main motivation of this research project is mainly to solve different problems in imaging, graphics, and visions. So there are many interesting problems in imaging, graphics, and visions. For example, denoising, in-painting, segmentation in image processing, surface reconstruction, texture mapping in computer graphics, shape analysis, classification in computer visions. So it turns out that all these problems, in our opinions, are quite related to geometry. So this motivates us to ask the question of whether we can find some geometry-based models to solve these problems. So in this research project, we are mainly interested in focusing on exploring the possibility to apply quasi-conformal geometry to solve these problems. So in summary, the goal of this research project is firstly to explore how quasi-conformal geometry can be computationally realized on discrete surfaces. By discrete surfaces, I mean triangular meshes or point clouds. And then the second part is we want to explore how QC geometry can be applied practically applied in real applications. So before we talk about how computational quasi-conformal geometry can be formulated and computed on discrete surfaces, let me firstly talk about some basic mathematical background related to quasi-conformal geometry. So first of all, what is a QC geometry? So quasi-conformal geometry is a topic in complex analysis introduced in about 1930. So what is a quasi-conformal map? So briefly speaking, quasi-conformal map is a generalization of conformal maps. So we all know that conformal map preserve angle, but quasi-conformal map allow angular distortion. So that's the main idea. So more specifically, a QC map is a homeomorphism with bounded conformality distortions, which satisfies the Beltrami equations. And this is the Beltrami equation, partial F partial C bar equal to mu partial F partial C. And the mu here is the Beltrami coefficients, which is the complex value function defined on the surface with supreme norm strictly less than 1. So it measures the local geometric distortion of the mapping. So, well, intuitively, so if you have a homeomorphism, orientation preserving homeomorphisms, the infinitesimal circles will be mapped to infinitesimal ellipse. And the distortion from the circle to the ellipse can be measured by the Beltrami coefficient. For example, the maximal scratching is given by 1 plus mu, and the maximal squeezing is given by 1 minus mu. So this is another geometric illustration of the idea. Suppose you have a triangle being deformed to another triangle. So if the Beltrami coefficient is equal to 0, then the angle is preserved. But if you increase the magnitude of the Beltrami coefficient, then you see that the distortion is getting more and more severe. So the take-home message here is that if the Beltrami coefficient is equal to 0, then this is conformal without local geometric distortion. When mu is bigger and bigger, then it's introduced larger and larger distortion. When mu is equal to 0, actually you have partial F partial C bar equal to 0, which is exactly the Cauchy-Riemann equation, which is the conformal mapping. So this is the geometric illustrations of a pre-QC mapping. So we have the original surface. On the original surface, we draw some circle packing pattern on it. So under conformal parameterization, you see that infinitesimal circles are mapped to infinitesimal circles. But under quasi-conformal parameterization, you see that circles are mapped to ellipse. That means it's introduced local geometric distortions. So in terms of Riemannian matrix, under conformal mapping, the Riemannian matrix is preserved up to a scaling factor, and the lambda here is called the conformal factor. But under the quasi-conformal mapping, the Riemannian matrix is distorted by the Beltrami coefficient mu. So actually in this work we're going to use this is actually the formulation of quasi-conformal mapping in terms of Riemannian matrix, and in this work we're going to use these formulations to define the discrete formulations of quasi-conformality on discrete surface, and also use this Riemannian matrix formulation to derive some computational algorithm to compute computational quasi-conformal maps. So another important piece of information is the measurable Riemann mapping theorems. So this theorem basically say that there is under suitable normalization, there is a one-to-one correspondence between the collections of homomorphisms and the collections of Beltrami coefficients. So the idea is, if you give me a mapping, of course I can compute the Beltrami coefficients from the Beltrami equation. This gives you the distortions. But conversely, if you give me the Beltrami coefficients, I can find the associated quasi-conformal map whose Beltrami coefficient is actually equal to the given Beltrami coefficient. So there is a one-to-one correspondence between homomorphisms and Beltrami coefficients. So here is an illustration. So you have a homomorphism between different domains. For example, here is the rectangular domain, and then you have a surface mapping here. So for both of them, we can compute the Beltrami coefficients. Well, since the Beltrami coefficient is a complex value function, so the color map here is actually given by the magnitude of the Beltrami coefficients. So from the Beltrami coefficient, we can reconstruct the original surface map, the mapping, QC mapping. So this is the reconstructed mapping, and then you can see that the reconstructed mapping closely resembles to the original one. Okay, so this is sort of the basic ideas. Okay, so these are some of the basic mathematical background about quasi-conformal geometry on smooth manifold. So now, in order to practically apply QC, so we have to formulate quasi-conformality on discrete surface. So I will first of all talk about how we can formulate quasi-conformality on discrete surfaces. Then I'm going to talk about some computational algorithm for computing the QC map. So with the advances for 3D acquisition technologies, so currently it's very easy for us to obtain 3D geometric objects by different 3D scanning devices. For example, Kinect. So two of the commonly used digital representation of the 3D shapes can be triangular meshes or point clouds. Okay, so in this way we're going to focus on triangular meshes and point cloud as our 3D shape representations. Okay, so now in order to practically apply QC on discrete surfaces, we need to give a discrete formulation on QC on discrete surface. So on triangular meshes, the discrete formulations of quasi-conformality is based on the discrete matrix. So we call that on the smooth manifold, under quasi-conformal map, the matrix is distorted under the mapping by this formula. Okay, so in other words, you see that the Riemannian matrix is distorted by the Beltrami coefficients. So if you look at this formula, so if you modify the matrix on the source surface, the original surface, to dc plus mu dc bar, then you can actually see that the Riemannian matrix under the mapping F, the Riemannian matrix is preserved up to a scaling factor, which means conformal. So in other words, what is the take-home message here? The take-home message here is that, well, originally you have a matrix on the surface, but if you modify the matrix on the surface, a quasi-conformal mapping becomes a conformal mapping. So that's the idea. So we boil down the problems of computing quasi-conformal mapping to computing conformal mapping. So this is a simple idea, but we're going to use this idea to give the discrete formulation of quasi-conformality. Okay, so first of all, what is a discrete matrix defined on a triangular mesh? So very simple, a discrete matrix on a triangular mesh is just a positive value function defined on the edges that satisfies the triangle inequality. That means the edge length. So with the notion of discrete matrix, then we can talk about the definition. We can talk about discrete conformal deformations. We can talk about discrete conformal deformations. So suppose we are given a deformation between meshes. Suppose the mesh is deformed by the deformations to another mesh, such that the original edge length, little Lij, is deformed to another edge length, capital Lij. We say that this deformation is discrete conformal if the capital Lij is equal to the original edge length, little Lij, multiplied by some factor. And the factor is actually determined by the two vertices of the edge. So, and then this factor is called the conformal factor. So in other words, discrete conformal deformation is just a deformation which preserves the original matrix up to a scaling factor, which is consistent with the definition of conformal deformation in the continuous setting. So now with the notions of discrete conformal deformation, we can talk about the definitions of quasi-conformalities on discrete surface. So the definitions of discrete quasi-conformal mapping is just as follows. So suppose you are given a mapping between two triangular meshes, we call it F. Okay, so we say that this mapping F is a discrete quasi-conformal mapping with Beltrami coefficient mu if under the modified matrix this is a discrete conformal mapping. And then the modified matrix is actually given by this formula. It's actually given by this formula. Okay, so you see that this formula is exactly consistent with the formula in the continuous case. So you see that, so this definition is nothing but just saying that the discrete quasi-conformal mapping is just a discrete conformal mapping under the modified matrix. So that's the idea. So which is actually the consistent definition with the continuous case. So with this discrete definition, we can actually prove the consistency between.
What is an isothermal coordinate?
I'm sorry.
Can you
Busy?
remind us? Tell us what is an isothermal coordinate?
Oh, basically, just locally, you can actually isometrically or conformally embed the surface onto the parameter domain, and then this gives you the coordinate, and then it gives you the matrix. That's it. But
give an example.
Well, locally you have mesh, a surface mesh, and then you can locally compute the local conformal parameterization of the mesh, and then this gives you a coordinate, and then you map it to the 2D, and then you have DC and DC bar, and then it gives you the matrix.
So will barycentric coordinates in the triangles?
We don't use barycentric. We use
Is it isothermal?
no, we use conformal. Yeah, we use conformal. Yeah, angle preserving.
So your Beltrami coefficient mu ij.
Yeah.
It's mu I plus mu j half.
Mm.
So mu ij is a metric, and mu I and mu j is a function.
Yeah, because
So if you compare with your original formula, it looks like you have introduced a differential here. So why does this correspond to the original formula?
Oh, because basically the Beltrami coefficient is defined on the vertices.
Yes.
On the vertices.
Yes.
And then because the edge, so when we talk about the edge length, when we talk about this discrete matrix, the discrete matrix is defined on the edge length, on the edges. And so you have to find the Beltrami coefficient on the edge. And so what we do is just take the average.
This is a geometric transformation, and how do you
Yeah.
justify it?
What do you mean?
I mean, what are you doing here geometrically?
Geometrically, we just use the Beltrami coefficients you just use the Beltrami coefficient on the two vertices to distort the average of the Beltrami coefficients on the two vertices to distort the edge length based on the Beltrami coefficient. But anyway, we can actually show that with this discrete definitions, there is a consistency between discrete quasi-conformal mapping and continuous quasi-conformal mapping in the sense that as the mesh size tends to 0, this discrete quasi-conformal mapping is actually converged to the continuous quasi-conformal map.
That's because you have
Yeah.
mean value.
Yeah, exactly. Yeah, sorry.
It's a new idea, so it's not
Yeah,
that's not present in the continuous.
Yeah, I'm sorry, Aaron.
Going back to this isothermal coordinate,
Yeah.
if you are given two vertices, so one line,
Yeah.
how much neighborhood do you need to estimate that?
Well, we just for
There are
example, because this is
local
we just take, well, in practice, it's just need a one ring neighborhood.
Yeah.
So we just take a two ring neighborhood and do the conformal parameterization.
But
Then.
there's no closed form formula that you could.
Yeah.
You have one.
Yeah,
the closed form formula. So
yeah.
it's not really that you have
Yeah,
to run a software.
yeah,
and
we
that-
don't
that-
actually. Yeah, you're right. Yeah. Okay. Okay, so this is, well, actually we also have a discrete formulation of quasi-conformality on point cloud, but because of time constraint, I don't think I will go talk about that. But I would rather talk about some computational algorithm for computing the QC map, because in order to practically apply this quasi-conformality for formal mapping or practical application, we need to know how to computationally compute the QC map. So over the last few years, we have developed different computational algorithms to compute the QC maps, and today I'm going to talk about three algorithms that we commonly use. The first one is something called the quasi-Yamabe flow method, or the quasi-Ritchie flow method. So this is the combination of the discrete Ritchie flow and the matrix multiplication to compute the QC maps. So the idea is very simple, because so if you still remember, according to our definitions of discrete quasi-conformality, you see that a discrete quasi-conformal mapping is just a discrete conformal mapping under the modified matrix, So in other words, if you want to compute the quasi-conformal mapping corresponding to some Beltrami coefficients, what we need to do is just, first of all, you distort the matrix on the original surface, and then the quasi-conformal mapping under this modified matrix will become a conformal mapping. And then we can just use some existing conformal mapping algorithm to compute the quasi-conformal mapping. That's the idea. So step one, given the original matrix Lij, we modify the matrix by the equation that we have introduced. Okay, and then under this distorted matrix, a quasi-conformal mapping become a conformal mapping. So what we need to do is just to compute the conformal mapping under this matrix. Okay, so and then in this work we try to use the discrete Ritchie flow to compute the conformal mapping. So what is a discrete Ritchie flow? Discrete Ritchie flow is the algorithm introduced by Hu and Yao. So the idea is to conformally deform the Riemannian matrix according to the Gaussian curvature, and then upon convergence we get a uniformization matrix. And with the uniformization matrix, we can actually we get the conformal embedding. So that's the idea, how we get the discrete quasi-conformal map. So the good thing about this algorithm is that discrete Ritchie flow it can be applied to surfaces of any arbitrary topologies. And this is the reason why this algorithm is good. So here we show some examples. So we have a simply connected open surface, and then we compute a quasi-conformal quantization with different values of Beltrami coefficients. When mu is equal to 0, then you see that it's exactly conformal. You see that infinitesimal circles are mapped to infinitesimal circles. But if you introduce different values of Beltrami coefficients, then you see that you have different quasi-conformal quantization. Infinitesimal circles are mapped to ellipse. And then, well, this algorithm can be applied to any surfaces of any topologies. For example, here you have the multi-connected surface, and then you can also compute the quasi-conformal quantization if you're given different Beltrami coefficients. Okay, so this is the first method that we use to compute the quasi-conformal mapping. Another method that we use that we may use is the so-called Beltrami holomorphic flow method. So this method is an iterative method which iteratively modifies the mapping according to the variation of the Beltrami coefficients. So the idea is actually very simple. Suppose we want to compute the quasi-conformal mapping associated to the Beltrami coefficient mu. So what we need to do is that we're starting from the Beltrami coefficient 0, which is associated to the identity mapping. So we iteratively modify the Beltrami coefficients until it's reached to the Beltrami coefficient mu. So in each iteration, we find the associated quasi-conformal mapping associated to the modified Beltrami coefficients. Okay, so of course here you have to find, in each iteration, we need to know the variation of the quasi-conformal mapping corresponding to the variations of the Beltrami coefficients. So it turns out that these variations can be obtained by the integral formula, and in the discrete case, you also have the summation formula. Okay, of course, the computationally is very time-consuming because you have to compute integral, and in discrete case, you're computing a summations. So later work actually not by me, by a professor at UCI. So he has actually solved this problem, try to approximate the variation by solving the least square Beltrami energy. So basically trying to solve the optimization problem of the least square Beltrami energy, and then you can approximate the variation, and then it's you can very much speed up the computational speed. So this is one of the experimental results. So we have originally we have this diffeomorphism, this homomorphism bijective mapping. Well, then we and then we want to, and then we can compute the Beltrami coefficient. And then from the Beltrami coefficient, we want to use this iterative algorithm to reconstruct the mapping. So you can see that as iteration goes, the error between the reconstructed mapping and the original mapping becomes smaller and smaller. That means it actually will iteratively converge to the quasi-conformal mapping. Okay, so well, the last algorithm that I want to introduce is the so-called linear Beltrami solver. So as you know, well, if you look at so this method is basically solving the PDE. So if you see, if you remember, the quasi-conformal mapping is just a it's just a mapping that satisfies the Beltrami equations. Okay, so if you play with this Beltrami equation, you separate into the real part and the imaginary part, and then you get these two equations. And then if you apply divergence on both sides, then you actually get elliptic PDE for each coordinate functions. So you have an elliptic PDE, and then subject to some suitable boundary conditions, then you get you can actually discretize this elliptic PDE, and then you get a sparse matrix, and then this matrix can be solved by a conjugate gradient method, which is fast. But this method can only apply to a simple domain, simply connected domain, because solving the PDE on a more complicated domain, for example, if you have a circular shape, then the equation become much more complicated. But anyway, this is the experimental result that we have, and again, with a mapping, and then you have the Beltrami coefficients, and then we can reconstruct it. But solving the PDE is much faster because, well, this is elliptic PDE, so it takes less than 0.1 second, and then you can obtain the mapping. Okay, so these are basically the computational algorithm which we used to compute the QC map from the Beltrami coefficients. So besides, we are also interested in a very special kind of QC mapping, which is called the extremal mapping. Okay, so what is an extremal mapping? So an extremal mapping is a QC map that minimizes the conformality distortions subject to the prescribed constraint. So without any constraint, there is always a mapping between two surfaces which is exactly conformal without any constraint. Right? Without any constraint between two surfaces, we can always find a mapping which is exactly conformal. But with additional constraint, for example, if for facial recognition, if I want to map my face to your face, then I have to enforce that my left eye map to your left eye, right eye map to your right eye, nose map to your nose, and so on. You have a lot of features correspondence constraint. With the additional constraint, the mapping between the two surfaces, which is exactly conformal, may not exist. Right? In that case, what we want to do is to find a mapping which minimizes the conformality distortions subject to the prescribed constraint. Or more specifically, what we want to do is to minimize the Beltrami coefficient in the L infinity sense. Okay, so if you're given the interior landmark constraint, extremal mapping always exists. Okay, so in other words, extremal mapping can be regarded as the most conformal map subject to the prescribed constraint. Okay, so closely related to the extremal mapping, is something called the Teichmüller mapping, T-map. Okay, so what is the Teichmüller mapping? A Teichmüller mapping is a QC map with uniform conformality distortions whose Beltrami coefficient is of this form, where k here is a positive constant strictly less than 1, and phi here is a holomorphic function. So if you look at this quantity, phi bar divided by the magnitude of phi, this gives you the angle of the Beltrami coefficients. And then if you look at the magnitude of this complex value function mu, this is constantly equal to k. So in other words, the T-map has uniform conformality distortion over the whole domain. Okay, so this is the ideas of T-map. So here is an illustration. So you have a general QC map, then you can see that the eccentricity of the ellipse are not uniform over the whole domain. If you look at the histogram of the norm of the Beltrami coefficient is scattered, but under the T-map, the histogram of the BC norm is actually accumulated at a constant. So in other words, it means the distortion is uniform over the whole domain. Okay, so why do we talk about the T-map? Because under suitable conditions, the extremal mapping is actually the T-map. So what is the suitable conditions? The suitable condition is that the first derivative of the boundary corresponding is non-zero, and the second derivative is bounded. Then we can actually show that the extremal mapping is actually the T-map. So what does it mean? It means if you want to compute the extremal mapping, which minimizes the conformality distortion in the L infinity sense, you don't need to solve the optimization problem, which minimizes the L infinity norm, which is, well, I think it's very difficult to solve, right? So we can actually compute a T-map. We can actually compute a T-map. So mathematically, what does it mean by computing a T-map? Mathematically, computing a T-map is as follows. We want to solve the Beltrami equations, parcel F, parcel C bar, equal to a Beltrami coefficient multiplied by parcel F, parcel C, or subject to the landmark constraint, subject to the boundary constraint, okay? And then the Beltrami coefficient should be of Teichmüller type, because we want to compute a T-map. And the Beltrami coefficient should be in this form, K, and then multiplied by phi bar divided by the magnitude of phi. So if you look at this PDE, well, it seems to be simple, but actually it's not simple, because if you look at this PDE, the mapping F is unknown, the constant K is unknown. We don't know what is the K, and the holomorphic function phi is also unknown. So solving this PDE is not that easy. Well, and also solving the L infinity norm problem is not easy. So so in 2015, together with my collaborators, we're trying to solve this problem, try to find a T-map. So we introduced a algorithm called quasi-conformal QC iteration algorithm. So let me first of all talk about the intuitive ideas of this iterative scheme. So what we're trying to do is, okay, so initially, suppose you have a mapping, landmark matching mapping, which is not of Teichmüller type. So in other words, the Beltrami coefficient is not in this form. So what we do is we try to modify. We try to modify the Beltrami differentials. How do we modify it? We normalize the Beltrami coefficients to one with a constant norm. And then the constant is just taken to be the average norm over the whole domain. Okay? And then we do a Laplace moving of the Beltrami coefficient, and then we get the updated Beltrami coefficient. And once we get the updated Beltrami coefficient, we construct a QC mapping whose Beltrami coefficient is closest to your updated one. And then you keep the iteration going until it's converged. So the idea is very simple. You just iteratively modify the Beltrami coefficient such that at the end of the day, hopefully it's converged. Then you actually get a quasi-conformal mapping with uniform conformality distortion. So that's the idea. Okay, that's the idea. Okay, so this is the algorithm. In iterations, you do a normalization, a plus moving, and then you can update the Beltrami coefficients, and then we construct a mapping, landmark matching, quasi-conformal mapping, whose Beltrami coefficient is closest to the updated one, and then you keep the iteration going. Okay, that's the idea. Okay, so it seems to be very, very intuitive, right? But would it converge? Okay, so in 2015, we had together with David Gu and Xinchong Yao, we have proved that this QC iteration would converge to the T-map. So the basic idea is that we can actually show that this QC iteration is nothing but just the minimization of the harmonic energy under the distorted matrix given by the Beltrami coefficient. So if you're given a Beltrami coefficient, then you have this, you have a modified matrix, and then you have you can use the modified matrix to define the harmonic energy. So it turns out that the QC iteration is nothing but just the minimization, iterative minimization of the harmonic energy under the distorted matrix given by the PC. Okay, and then the minimizer is actually the Teichmüller mapping. Yeah.
How unique is the Teichmüller map?
How unique? Okay, so if the boundary, so I've actually mentioned if the first derivative is non-zero, and then the second derivative is bounded, then actually log proof by us is actually proved by Frigo. Okay, he proved that the T-map will be unique, and this is the unique extremal mapping. I think he proved it in 1976 in his paper in AMS.
So just by the boundary condition.
Yeah.
But then you have also landmarks inside.
You should consider that as a Riemann surface of finite types. Yeah, so that works.
That is also.
Yeah, but the uniqueness is not proven by us, so it's, we just use his theorems. Yeah, but
boundary conditions are pointwise, meaning that if you have a curve,
we have a curve.
You want to know exactly the parameterization of
the
you have to know the point
exactly. Yeah, so this is the iterative scheme with how we compute T-map, and let me show you some results. So, well, we can apply the T-map to compute the Teichmüller parameterization of multi-connected domain onto some canonical circle domain, and then you can see that the histogram of the BC norm is accumulated at constant 0.2, and that means this is really a T-map. And this is examples of landmark matching T-map. So we have two human faces with the same topologies, and then we have some features landmark right on the face, and then we want to find landmark matching mapping between them, which minimizes the conformality distortion in the L infinity sense. So we compute a T-map, and then this is a T-map that we get, and then this is the histogram of the BC long, okay, which accumulated at a constant. That means this is a T-map. Okay, so this is how we compute a T-map. Okay, so I've talked about how we can realize computational quasi-conformal geometry on discrete surfaces.
So it is a good thing that at the end you get a uniform distortion rather than something that could be. I mean, you just move one point and
so so different people have different tastes. Or actually, we try to sell this T-map idea to the medical people. They don't like it because the distortion is actually spread out on the uniform region. But if I talk to the graphics people when they want to do texture mapping, for example, they like it. So I'm going to show some example, and then
so you minimize, for example, the N1 norm of the.
I have tried actually. Yeah, I will show some example, and then you will see. Yeah. So this is actually a good question because we try to propose different model to different people, and different people give us this different feedback. So this is the reason why we have different models in the application part. Okay. So in the second part of my talk, I'm going to talk about some of the applications of QC in different for different applications for registration problems, shape analysis problems, and geometry processing problems. So let me first of all talk about the registration problems. Okay, so Lauren has already introduced the registration problems. So this is the main goal is to find a meaningful one-to-one correspondence between different data. The data can either be images or surfaces, right? So there are many important applications for image registration and surface registration. For example, image super resolution, video compression needs image registrations. For facial recognition, texture mapping needs surface registrations. So because of the importance of registration, so there are many different registration models proposed recently. So if you look at all those algorithms, so these algorithms can mainly be divided into two categories. The first category is the so-called intensity-based registration models, which is based on the registration is based on matching the image intensity for image registration or matching the geometric quantity, the curvatures for surface registration, for example. A landmark-based registration is trying to find a registration which is based on matching the features or landmark. For example, for brain, there are some important so-called landmark on the brain surface, and what we want to do is to find a mapping between the two brains that matches the features landmark consistently while minimizing the distortion. Okay, and then these features can be labeled by doctors. Okay, and I did my PhD at UCLA, and then the data that we got is some brain surface with all the so-called landmark labeled by neuroscientists. So these are the data I have. Yeah. So then what we want to do is to compute a mapping between the two brains that matches the landmarks. Okay. So using the quasi-conformal mapping, we can actually develop different registration models. Okay, we can develop a landmark-based registration model and also the hybrid and also the intensity-based registration model. Okay, so what is the idea? The idea is to solve the optimization problem over the space of Beltrami coefficients. So for landmark-based registration models, so we try to minimize this energy. We want to find a mapping which minimizes the harmonic energy of the Beltrami coefficients and the LP norm of the Beltrami coefficients. And usually the P is chosen to be 2, okay, because it actually makes the optimization easier. So the first term actually trying to improve the smoothness of the mapping, and the second term is trying to minimize the Beltrami coefficient such that the local geometric distortion will be reduced. Okay, so that's the idea. Subject to the landmark constraint and the bijectivity, the supreme norm of restricted less than 1. And you can actually incorporate the intensity matching term, mismatching term into the energy, so that your registration will also match the intensity. So that is a very simple idea. For geometric matching registration, you can actually incorporate the mean curvature and Gaussian curvature mismatching for surface registration that matches the curvature. Yeah, but then how can we optimize, right? How can we solve this optimization problem? So to solve this optimization problem, we use the splitting method to solve this optimization problem. So the idea is to introduce an auxiliary variable f into the optimization problem, where f is supposed to be the mapping associated to the Beltrami coefficient u. Okay, so we have a penalty terms here to couple the mapping f and the Beltrami coefficient u. So this is the problem that we want to solve, and then we try to alternatively minimize this energy. We fix nu minimize over f, and then we fix f minimize over nu, and keep the iteration going, alternating minimization. Okay, so this is the problem we're trying to solve. So fixing f, Okay, fixing f, then you have this optimization problem to solve. Okay, fixing f, then the Beltrami coefficient of f is also known, so this is just a constant. So you have to solve these optimization problems. If you compute the Euler-Lagrange equation of this optimization problem, it's just an elliptic PDE, right? Because this one becomes Laplacians and this one becomes 2 nu, and then you have 2 nu minus mu. So this becomes a elliptic PDE, which can be solved very efficiently. And then fixing the Beltrami coefficient mu, then this is the optimization problem that we need to solve. So if you look at this optimization problem, what we want to do is we want to find a mapping F such that the Beltrami coefficient is closest to your prescribed Beltrami coefficient subject to the landmark constraint, right? So we have introduced several computational algorithm to compute this mapping F, and then in practice we use the linear Beltrami solver to solve it. So this is linear and this is linear, so the whole algorithm is just a linear, in each iteration is linear, and then this is how we solve the problem. Okay, so let me show you some results. Okay, so it turns out that this Beltrami coefficient can effectively control the bijectivity. Yes.
So suppose you have found your Teichmüller map,
Yeah.
and you have now this Beltrami coefficient.
Yeah.
Does this give you a sort of distance? I mean,
I will talk about it. Yes, Teichmüller distance.
The Beltrami coefficient is a space of holomorphic functions.
Yeah.
So your distance takes values in a space of holomorphic functions,
Yeah.
and how do you extract a distance from this?
Well, I will talk about that in the shape analysis part. Actually, we use the Teichmüller distance. This is a very good point because the Teichmüller mapping will give you the Teichmüller matrix. Yeah, I will talk about that in a moment. Yeah. But anyway, let me show some examples of QC registration model. It turns out that the Beltrami coefficient can effectively control the bijectivity. Okay, so here is an example. So we want to find the mapping, okay, landmark matching, mapping, okay. So and then we try to, the landmark will be just rotated by 180 degrees, okay. So we want to find a mapping, a landmark matching mapping, and then the landmark is actually rotated by 180 degrees. This is a really, really large information. And then you see that using our algorithms, the bijectivity is preserved, even under this very large deformations. And this is incorporating the intensity matching. So you see that we try to deform the letter I to the letter C, and then if you look at the grid here, actually the bijectivity is preserved using this Beltrami coefficient. So this tells us that by incorporating the Beltrami coefficient in the regularization term, as a regularization term in your registration models, is preserved the bijectivity very effectively. Okay, so we apply this for brain mapping. Okay, so if you use conventional method to compute the landmark matching brain registrations, the bijectivity can usually cannot be avoided, cannot be preserved. So you can actually see some frips and overlap using the conventional method. And using our method, we can actually deform the brain surface, and then the frips and overlaps are avoided. Yeah, so we apply this for computing the landmark matching brain registrations. We apply this to compute the registration between hippocampal surface by matching the mean curvature and Gaussian curvatures. And we use the T-map to compute the registration between the brainstem. Yeah, and then this is the mapping that we get. And then this T-map algorithm can also be extended to genus 1 surface or high genus surface. So this is a genus 1 surface, and then we can also compute the Teichmüller registration between them. Okay, so and then in graphics application, we actually apply the Teichmüller mapping to do texture mapping. So suppose you have two surfaces, and originally you don't have any texture on it. You want to decorate the surface, okay? So what we can do is that we want to project an image onto the surface, right? So you have some corresponding features on it, and then you want to find a mapping between the surface and the image, and then project it back, right? And then you can decorate the surface, and then this is what we get. Yeah. So this is for graphics applications. Yeah, and then we can, in some situation, you know that conformal mapping is actually sort of opposite to area preserving, right? So you have a conformal map, then area may be distorted, right? Because conformal may distort the area. So what we want to do in here is that we can actually incorporate the area mismatching terms into your energy functional, so that we can actually get a QC map that minimizes conformality distortion and area distortions. Yeah. So here we just the regularization term on the Beltrami coefficient remain the same. And then the area mismatching terms, we make sure that the Jacobian of the QC map will follow the prescribed area distribution. So you can actually assign, okay, for example, that part has to be larger, this part will be smaller, then you can actually prescribe different area distributions. Then we can obtain a QC map that follows the prescribed area distribution as good as possible while minimizing the conformality distortion in the L2 sense. So in the L2 sense, not L infinity sense. So the conformality distortion will not spread out over uniformly over the whole domain. Well, in some situations, for example, texture mapping, this may be useful. For example, if you just use a conformal parameterization, right, to parameterize the surface, to map the surface onto the texture image and then project it back, then you can actually see a lot of unnatural distortion. But if you balance between conformal and area, then actually you can get a much more natural texture mapping. Okay, so this is the reason why sometimes we may want to incorporate the area into the framework. Yeah, and then we can use it for probing design or for visualization for medical anatomical structures. If you use conformal parameterization, parameterize it onto the 2D domain, then you see a lot of area distortion squeezing. But if you use conformal area, then actually you can the area distortion will be much less. So this is like balancing area distortion and conformality distortions. Yeah. So another interesting application that I want to show is well, this QC mapping can be laterally used for image retargeting problem. This is for image processing. So what is an image retargeting problem? So image retargeting problem is to resize an image to another image with the prescribed aspect ratio. For example, originally you have this image and then you want to resize it to the image with this aspect ratio. Okay, so if you use a simple scaling, then the image object will be distorted, right? So like this is much distorted. So in other words, to solve this image retargeting problem, what we need to do is that we have to find a deformations from one image to another such that the object region will not be distorted. Okay, so using the barometric coefficient, we can easily control the distortion of the mapping at different regions. For example, the barometric coefficient of an affine mapping is just a constant, right? A BC of a simple scaling map is just equal to 0. So what we can do is that if you have an image, you look at the object region, you enforce the object region to be simple scaling with barometric coefficient equal to 0, and then you can allow the rest of the region to have some distortion, but not too much. Okay, so you try to minimize the barometric coefficient for the rest of the region, and then you get the barometric coefficient, and then you can get the mapping. Okay, so this can be used for image retargeting. So if you have an image, you want to retarget it to the image with this aspect ratio. So if you use a simple scaling, you see the distortion of the car. And then another famous algorithm is called sim-proffing, and then you can see the distortion of the car. And using the QC map, you can actually preserve the structures. Well, this is another example: scaling, sim-proffing, and then this is our method. Well, we want to resize this image to this, right? And then this is simple scaling. You see the object is much distorted. Sim-proffing is a little bit better, okay? But this is the result that we get. And then this can also be applied to a more extreme case with very large aspect ratio. Yeah, so you can actually see that this also works, and it also works for the
Very strange.
Yeah.
Wow, this
Yeah. Yeah, but this is just extreme examples, showing that this works. Yeah. So how many minutes do you have?
About 10.
Okay,
We'll
good.
fly for questions.
Okay, yeah. Shape analysis problem. So I have to answer your questions. Well, what we want to do is that given two surfaces, we want to detect abnormal deformation or locate geometric differences between the two surfaces. Well, in particular, in medical imaging, biological organs are usually geometrically very complicated. So using human eyes to look at it is very complicated. So we wanted to, for example, here it is a brain which undergo gyrification. So for it's a patient with Williams syndrome disease. So if you just look at these two brains, you cannot see the gyrification. But if you zoom in, you can see a little bit. So what I want to say is that if you just use human eyes to locate the geometric distortion, it's very complicated. So we want to develop some models to do it. So for the shape analysis model, so we can actually combine the barometric coefficient with the curvature mismatchings to obtain a complete shape index. So for that one, you can actually prove the rigidity properties of this shape index in the sense that if you can find a mapping F such that the energy is exactly equal to 0, then the two shapes are equal up to rigid motion. Okay. So in other words, what we can do is that we can find a mapping F that minimizes this energy. Okay. And then the mapping will be the geometric matching mapping. And then with the mapping F, then you can use these functions to get the values on every vertex on your surface. Okay, so larger the values, then you have more geometric differences between the two surfaces. And this gives you a visualization tool for us to find out the local geometric distortion.
H and K?
H is a mean curvature and K is Gaussian curvature. So the mu with K will give you the isometric matrix, and H will give you the embedding. Yeah, so that's the idea. Well, and then you see that this is the hippocampus surface of surfaces of two normal subjects, right? And then this is the hippocampus surface of a normal subject and Alzheimer's disease patient. So you actually see that the geometric differences between normal and Alzheimer's disease is much more different than the two normals. Well, this may not be very meaningful. So what we have done is we try to use this energy, this method, to study the temporal shape changes of the hippocampus surfaces. What we try to use is we use the Atlee data. We use the Atlee data to look at the hippocampus surface at time equal to 0 and at time equal to 12 months. Okay, so after 1 year time. Okay, and then we try to measure the temporal shape change of each hippocampus surface. So for normal subject, the temporal shape change is not that much. But for Alzheimer's disease patient, you can actually see more significant shape changes. Okay, so this is how we can use this quasi-conformal geometry to do shape analysis. Well, the second thing is to answer your questions, right? So we have a way to compute the T-map, Teichmüller mapping. So can we use the T-map, okay, to define some sort of matrix, right, distance matrix? So it turns out that yes, okay, so we can actually use the T-map to compute a Teichmüller matrix. So suppose you are given two Riemann surfaces with features landmark labeled on them. Okay, so we can actually define a distance between the two Riemann surfaces, Mi and Mj, by this optimization problem. You try to minimize the dilations of all landmark mapping between the two Riemann surfaces. Okay, you try to minimize this problem. So in other words, the optimization problem is over all the mapping. And then the dilation is actually defined by the Beltrami coefficient, the L infinity norm of the Beltrami coefficient. You think about this optimization problem is super difficult, right? Because the Beltrami coefficient is defined as Paso phi C bar, Paso C bar phi, Paso phi C, right? So basically, so this is a difficult optimization. And also you have L infinity norm and then optimize over all the mapping. But what is the good news? The good news is we can actually, they actually show that the minimizer of this optimization problem, the optimizer of this optimization problem, exactly the T-map. It's just the T-map. Okay, so what does it mean? In other words, in order to compute a Teichmüller matrix, we don't actually need to solve this optimization problem. We just compute the T-map between the two surfaces, compute the Beltrami coefficient, you get dilation, and then it gives you the distance. And then this is the Teichmüller distance between two Riemann surfaces with landmark label on them. So we use this to do some facial classification. So we have a collection of human faces with different expressions, point cloud surfaces. Point cloud surfaces. This one is point cloud, but we haven't talked about how we compute T-map on point cloud, but we have a way to do it. Okay, so point cloud surfaces, point cloud faces with different expressions. This is some of the example of these faces. And then we try to compute the pairized Teichmüller distance between any two surfaces, and then you do the MDS, and then you do the classification, and then just very simple machine learning classification algorithm, and then we already achieve 94% classification accuracy. Yeah. So this is how we use Teichmüller matrix to do shape analysis. Well, for geometric processing, I just want to mention one application, very simple thing. So if you have a point cloud surface, you can compute a mapping, parameterization to a simple domain. That minimizes the conformality distortion. Then on the simple domain, you can actually do a triangulation, and then you can pull back the triangulation to the original surface, and then you can get the meshing. So you can build a triangulation mesh on the point cloud. And this is another example. You have the soda can, and then map it to a simple domain by minimizing the conformality distortions. And then on the simple domain, you build the triangulation mesh, and then you can put the conductivity onto the original surface, and then you can do the mesh. Yeah. So well, I think I will I'll come to my conclusions. So in conclusion, I have described the discrete formulation of quasi-conformality on discrete surfaces based on discrete metrics. And then I've described different computational methods for computing the QC. And then we have shown some different applications of QC geometry in imaging, graphics, and visions. So with that, I think I will stop here. Thank you very much.
Thank you very much. Again, tough question.
So this Teichmüller distance that you had in the end,
Yeah.
I guess it's a geodesic metric space.
Mm-hmm.
And
The
does it
geodesic
have curvature, or can you compute curvature?
No, not at this moment, not yet.
Not yet.
Yeah, not yet. Yeah, not yet.
So there is no,
But the
no
geodesic-
Riemannian interpretation. This is not a Riemannian distance for a background.
It's not Riemannian.
No,
Yeah.
no.
Yeah.
I have a small question about this comparison of the different surfaces in the for the Alzheimer's disease.
Yeah.
So you have different kinds of variability, right? There's the variability that exists in the normal subjects, and you have the changes that exist in the
Yeah.
subjects with the disease. Yeah. So how do you factor out the two kinds of variability here?
Well, I talked to the doctor. They actually say that this one may not be so meaningful because even for normal subject, the shape can be very different.
Right.
So they actually do not trust this. So what they like is actually the temporal change. So given one subject, you look at the longitudinal data, you look at the shape at different time, and then you try to measure the temporal change. I think they like this more than the well, at least what I heard from the neuroscientists. Yeah.
The temporal change also you have like the change that can happen in the normal subject versus the change that can happen in the.
Yeah.
So is there a way to kind of
Back
factor
out.
that out?
So far we didn't do this kind of factorization of it. We usually just compute the p-map, the p-map on, and then you look at the statistical significant region. So we haven't thought about how to factor out the normal deformation, I guess.
For which test do you compute the p-map?
Which day?
Which test? Which statistical test?
Just a simple t-test. Yeah.
And you correct from multiple
Yeah.
It's very studied. It's kind of surprising.
Yeah. But this is the work that we've done. A few years ago. 3 or 4 years ago. Yeah.
A trivial comment about these important diseases versus unimportant diseases. You can probably make a lot more money by explaining to people who have broken their knee or hurt their knee how much their swelling has gone down.
Oh, really? Okay.
Because people care about either sports injuries and will pay for it.
Oh, really? Okay. Okay. Try to make an abstract.
On higher dimensional problems, image data, say, where Beltrami might be called defined.
Yeah. Actually, recently we have been. This is actually our current work. Right? We have a current work. Actually, the paper is already published in Journal of Scientific Computing. So we have a quantity trying to approximate the Beltrami coefficient in the two-dimensional. Because Beltrami coefficient is just for two-dimensional Riemann surfaces. Yeah, but we have the quantity which actually simulate the dilations in the two-dimensional case. And for that one, we have some extension, but it's still an ongoing work. Yeah. But the current model on the n-dimensional, we can already develop a registration model which preserve bijectivity by incorporating this new definitions of n-dimensional quasi-conformality. we can preserve bijectivity. Yeah.
Right, well, if there are no more questions, thank you again.
Thank you.